3.8 Derivatives of inverse trig functions. Your objective for this lesson is to find and apply derivatives of inverse trigonometric functions. This should be a fairly short lesson. Okay, so you can see this is a theorem, derivatives of inverse functions, and this says that if f is differentiable at every point of an interval I, and df dx is never 0 on I, so the derivative is never equal to 0, then the function f has an inverse, and f inverse is differentiable at every point of the interval f of I. So if your function is differentiable on whatever interval, and the derivative is not equal to 0, then the inverse is also differentiable. Okay, this is the derivative of arc sine, so d dx arc sine u is equal to 1 over the square root of 1 minus u squared times du dx, so long as the absolute value of u is less than 1. First example asks us to find d dx of arc sine of x squared. Let's give this a shot here. So we just established that d dx of arc sine u is 1 divided by the square root of 1 minus u squared times du dx. Okay, and here my x squared is my u. And you should recognize this is a chain rule problem also, so we have an inside function. d dx of arc sine of x squared is equal to the derivative of the outside function is our definition over here. Okay, so just plugging this in. And you'll notice that I put in x squared squared, even though this has a 2 for the exponent. I need to square that also because it says u squared, and the x squared is just in u's spot, so I have to square my u. Now I'm multiplying this by the derivative of u, so d dx of x squared. Okay, working this out a little bit more. I know that x squared squared is x to the 4th, and the derivative of x squared is really 2x. Last step, I can condense this. 2x is really 2x over 1. I'm going to multiply my fraction straight across. So 2x divided by the square root of 1 minus x to the 4th, and this is my derivative. Next up, derivative of arctan is 1 divided by 1 plus u squared times du dx. This one you should definitely memorize. This is probably the most important of your inverse trigonometric derivatives. Example 2. A particle moves along the x-axis so that its position at any time t is greater than 0 is x of t, so x is the position as a function of time, equals arctan of the square root of t. So again, square root of t is my u. What is the velocity of the particle when t equals 16? Okay, so recall that the derivative d dx of arctan u is 1 over 1 plus u squared du dx. Okay. And in this case, we have a position function, x of t. We want to know the velocity. Remember, velocity is the first derivative of the position function. So this is x prime of t. That's what we're looking for. So basically, we're looking for the derivative of this, arctan of the square root of t. So we want d dx of arctan square root of t. Okay, so let's plug it in. We have 1 over 1 plus, my u is the square root of t squared, times d dx of the square root of t. Now, square root and square are going to cancel. So I'm left with 1 over 1 plus t for the first part of this. The derivative of square root of t, well, this is really t to the 1/2, is going to be 1/2 times t to the negative 1/2. Which I can rewrite again. Remember, negative exponents I can rewrite on the opposite side of my fraction bar. So that would move down there. So I have 1 over 1 plus t times 1 over, I have a 2, and now I have my t to the 1/2, or square root t. Okay, this is the derivative. I'm not going to clean it up anymore because what I ultimately want to do here is plug in a 16 for t. Remember, t equals 16. T equals 16. So let's go ahead and plug it in. I have 1 over 1 plus 16 times 1 over 2 times the square root of 16. Okay, so this is 1 over 17. Okay, so we're going to have 2 times 4 here. Okay, and you're going to multiply top and bottom straight across. So we have 1 on top, and 17 times 2 times 4 is 136. So this is our velocity. We don't have a unit, but 1 over 136 is the velocity of this particle. Okay. Your last inverse trig derivative. We have d dx of arc secant u is equal to 1 over the absolute value of u times the square root of u squared minus 1 du dx. And again, the the absolute value of u will be greater than 1 here, which is actually different than arc sine. In the first inverse trig derivative you looked at, you had to be less than 1. This one's greater than. Example 3, we want to find d dx of arc secant of 5x to the fourth. So our derivative that we looked at, d dx arc secant u equals, this is a messy one. Okay. We're going to plug in, my u is right here, 5x to the fourth. So d dx arc secant 5x to the fourth equals, okay, 1 divided by absolute value of 5x to the fourth times the square root of 5x to the fourth minus 1. Oh, and I forgot to include on here du dx. Okay, so times d dx of 5x to the fourth. Okay, so this is always going to be a positive number because 5 is always positive, it's always 5. And x to the fourth, since this is an even exponent, that's also going to always be a positive number. So I can really get rid of these absolute value bars. And this was supposed to be squared. Sorry. So that's squared. So I have 1 over 5x to the fourth times 25x to the eighth, because x to the fourth squared will give you x to the eighth. You have to multiply those exponents, minus 1. And the derivative of this, I'm going to push my 4 down to the front. 4 times 5 is 20x cubed. Okay, it's over 1. So, simplifying this, up top, 20x cubed, you just multiply straight across. Same on bottom, multiply straight across. We have 5x to the fourth times the square root of 25x to the eighth minus 1. Okay. This is going to stay, the radical is going to stay as it is, but outside the radical I see you have a 20 and a 5, and 20 goes into 5 4 times. I also have these x's. If I simplify them, all these are going to go away, and I only have 1 x left on the bottom, which gives me my final answer here of 4 over x times the square root of 25 x to the eighth minus 1. Okay. And there you have it. That is it for 3.8.